Are there any questions, either about assignments, about projects, about, anything from the last lecture before we start off? Nope, I don't see any questions. So I guess that means we can start. Okay, so the outline for this lecture is, we ended the last lecture with some discussion about forward and reverse scale. We'll pick up from there. We'll look up at some techniques for uncertainty estimation. Then we'll jump into sim to real transfer, and then look at some methods for few shot learning. Right? So let's jump into it. So one thing which will happen quite a bit in sensory motor learning, but also in machine learning, is suppose you're giving some distribution p, and I want to find a distribution q with parameters theta, which models p as closely as possible, right? So one distance measure we can use for this is a KL divergence, right? So it turns out that KL divergence is asymmetric, that depending on whether it is p q theta or q theta p, that have different interpretations, right? So if we look at what the forward KL, so one is called the forward KL and other is called the reverse KL, right? So let's look at what do these things mean, right? So it turns out if you do forward KL, then if you end up estimating q theta, you end up matching the mean of the distribution p, right? And mathematically this is how it looks like, right? And I'm just opening it up, I'm just writing the expectations. Versus if you look at the reverse scale, the reverse scale ends up choosing one of the modes of the distribution, right? So forward scale is capturing the mean and reverse scale ends up capturing the mode. So depending on what you care about, forward, so you can use forward scale or reverse scale, right? So we can again open up reverse scale also, and this is the form that we end up with if we end up opening reverse scale, right? Okay, so now why am I spending time on this? So one reason will become clear, and that reason goes as following. So consider this term on the top right, corresponding to forward care, right? This term ends up being the expectation of log of q theta x, right? And suppose minimizing the KL distance is same as maximizing the negative of the KL distance, right? Which will come out to be this term. And on the other side, the same thing I can do with reverse scale. Instead of minimizing the reverse scale, I can maximize the negative of it. So it comes out as the following term. Now if you compare this term over here, which is expectation of px log q theta x, this looks, so if you were to maximize this term and take the gradients, this pretty much looks very similar to the loss function you would use when you're doing supervised learning, right? So in supervised learning, you're taking the expectation with the ground truth data that you are given, and you want to maximize the log likelihood of your ground truth data, right? So it's maximum likelihood estimation. So that corresponds to doing forward KL, right? Versus if you look at what the reverse scale looks like, just assume that px, I express px as the reward, right, or r of t. Then, and your q theta is your policy, right? So then it comes out to be, we are trying to maximize the sum of rewards plus an entropy penalty on my policy, right? So reverse scale in some ways is the max entropy are like objective, right? So one way to think about is when you're doing supervised learning, you're maximizing the forward scale, and when you're doing reverse scale, when you're doing reinforcement learning, you are doing the reverse scale, right? So one thing to note is, in forward scale, the expectation is respect to p of x, which is the ground truth distribution, right? So ground truth is given to you. Whereas in reverse scale, the expectation is with respect to q theta x, right? Where you're learning q theta x. Right? So in some ways, in reverse scale, you're taking the expectation with respect to data you are collecting, right? And versus in forward scale, you're taking the expectation with some ground truth. So this is, something which is, need to know. First, that forward scale is mean. It estimates, it matches the mean of the distribution, and reverse scale matches the mode. And second thing is the connection of forward and reverse scale with supervised and reinforcement learning. So this is something which will come in handy in later parts of the course. So this is just something to know for now. So now before I move forward, now I'll just pause and see if there are any questions on forward scale, reverse scale, or these connections. So Dongchi has a question. It says, would it be possible to say forward is off policy learning? Not necessarily, right? Even in off policy learning, you can still collect data. It is just a case that the policy you use to collect data is different from the policy. Sorry, I mean, the policy to collect the data could be different from the policy that you are learning. Right? So I think if you are doing imitation learning, then you could say you are doing forward scale. But if you are collecting data and you're taking the expected and you are including that data as part of your optimization, then you are doing you know something more like reverse scale. Any more questions or any comments over here? Nope. Okay. So then let's jump into the second, again a miscellaneous topic which will keep coming up. So let's look at uncertainty estimation, right? So there are two types of uncertainty. We'll discuss one type now, and another type we will discuss, in a couple of lectures. So one thing that we typically want to know is how confident I am about the machine learning classifier or the policy that we have estimated. Now, what do I mean by that? Let's suppose if this represented the entire data set where X is my input and Y is my output, right? It's a simple example. But the reality is we never have access to the complete data set. So we have access to some part of the data set. For example, we might have got the data points which are denoted by dark blue, but we may not have gotten the data points in light blue, right? Or we could have gotten this data set, right? So we can never get the entire data set, right? In context of reinforcement learning, we may not sample all state action pairs, right? We are only sampling a subset of them. So now, suppose if I got this data set and if I learn a predictor from X to Y, maybe I end up getting W hat 1. But if I got this data set, the kth one, then my estimator is W hat K. Right? So depending on the data set I get, my estimators can be different. Right? So a natural question is, given I have a finite data set, how how much confidence do I have on the estimator that I have learned, or Equivalently, you could ask, how close is the estimator that I have learned to the ground truth estimator, right, which is W in this case, right, which would be the ideal mapping if I knew all the entire data set, right? So now, why is this important? So consider, Q learning, or consider any actor critic methods, right? So in actor critic methods or Q learning, we are optimizing actions with respect to the Q function, right? Or we are optimizing the actions with respect to the critic, right? So we want to be confident that the critic that we have learned is actually modeling my true critic, right? Now, because we have only sampled a subsets of states and actions, my critic may not be accurate. So we might want to know how confident I am in the value estimate of the critic. So, this is where this will show up in context of control. But this also shows up, quite a lot if you were also doing simple supervised learning, because you might ask the question, how confident I am about my model correctly uh, capturing the data that has been provided to me, right? Or does my model able to recover the ground truth hypothesis from which the data is generated, right? So, the same thing I've illustrated over here. Maybe if you had Q functions, Q1, depending on what data set I could get, I could get either estimate Q hat 1 or Q hat K, and we want to know how close we are to the ground truth Q function, right? So now, because we don't have access to ground truth data, how do we go about, um, measuring this confidence value? So one idea which is quite popular is this idea of bootstrapping. And the main intuition is that we artificially create, some of, um, so we artificially create subsets of data, right? So for example, and assume that instead of this being the entire data set, this is the data that we actually have. Now what I can do is I can create data sets from this by sampling this data set, but I'm going to, sample with replacement. What this means is, I might get some data points can be sampled multiple times, and some data points I'm not going to sample at all, right? So, I get sample one, and similarly I can, get the kth sample. So what this is emulating is the fact that, the data I have is some subset of the entire data, but because I don't have, access to the entire data, how do I estimate the confidence, right? One thing to do is, well, I have some data, I can artificially create, some small subsets of data, and then estimate, classifiers or predictors on those different small subsets, and measure how different are those estimators. If those estimators are not very different, that would mean that I have high confidence that I am close to my ground truth estimator. But if I find that these estimators like W hat 1, W hat K are very different from each other, then that would mean that I'm not very confident on the estimate I have. Right? So, similarly, so what you end up doing is we end up measuring the variance of the estimates in these data sets that we generated by doing sampling. Right? So, does this make sense of, what, how are we measuring the confidence of our predictors? Any questions on this part? No. Okay, I see one question, popping up. Okay, so the next practical question which comes up is, how do I, suppose I got some data set and I artificially created some samples, like k different samples. How do I estimate this w hat 1, w hat k? Right? So one strategy is that we use different neural networks to estimate the, say, the w hat or q values for these different data sets, right? So now suppose I get some state action pair. I have k neural networks. I predict the q value from all of those k networks, and then I measure the variance in them, right? And that is going to give me an estimate of how confident am I on the measure of the q value for that state in action. Right? So, instead of having a separate network to save computational cost, it is also common to have your input, which is the frame of the image over here, have some shared part of the network, and just have k heads, right? For example, you can just have k last layers, right? So you can just have k heads at the last layer, or maybe k heads with the last two layers. So it's not necessary to have the entire network be separate. And what you can show is that if you use this method of measuring uncertainty, so over here what I'm showing, on the x and the y, so this y is the predicted value and x is the input, and these blue points are data points, right? And these gray lines are telling you how confident I am about, or the variance in my confidence, right? So what you see is where we have data points, the confidence is actually large, and in parts of the estimate where we don't have data points, the confidence is quite low, because you see the variance is quite high, right? So this technique of using bootstrapping to measure confidence is something which is very commonly used throughout deep learning and machine learning. Now, why are we talking about this? Think about using actor-critic methods, and the problem being that you don't know how good the critic is, but you are taking gradients with respect to the critic to find the optimal action, right? So if you knew how confident you are about the critic, that knowledge can be useful, right? Other place where we'll see uncertainty being useful is in exploration. That is something we'll look in a few lectures. But the idea being that if I am not confident about Q values in some particular states, then I want to explore in those states, right? Versus if I'm very confident about the Q values, then maybe I don't need to explore, right? So, that is another way where this idea of having a measure of uncertainty will be useful. A third place where this will show up is with respect to safety. Now, more on that later. But this is, again, a short segment on how we can measure uncertainty in deep networks. Okay, so now one question which is coming up is a random initialization plus variance in data only thing preventing the heads from being identical? That is true. So it is random initialization, and because you're sampling data, and those data samples come in different orders, which is a variance in data, that is exactly what causes networks to be different. Yeah. Any more questions on this? before we move forward? Okay, I guess if you have something, let me know. And if you're, really interested in this topic, there was a NeurIPS workshop in 2020 on uncertainty estimation, and it's a 3-hour workshop, but it gives you a very good idea, and it's very accessible the way the presentation was made to understand what is the latest and greatest in uncertainty estimation. It turns out bootstrapping is, among, it's pretty close to state of the art, if not the state of the art. So there are a couple of questions, coming up. There is a shared network for all different data samples. So Ayush, I'm not sure what your question is. If you want to maybe speak up, I can answer you better. In the meantime, I think Dongchi, you're asking, wouldn't this be computational heavy? Yes, I think if you have separate K networks, it's computational heavy. One way to go around is to share some part of the network and have some part of the network be different, as you see on the left part of your screen. That's one method. People have devised some other methods also to reduce the computational overhead, but I don't think you can go below having K heads at the last layer. I think you have to at least pay that cost.
Would the parallel computation be used for method to go over the computation overhead?
Yes, so if you can do parallel computation, you're going to save time, right? But not overall compute.
Yes, that's true. Thank you.
Yeah, sorry. So what I was asking was that if there are K networks, then like if there are K separate networks, then the uncertainty that we are modeling would be a function of both the initialization of the network and the specific data sample that the network is trained on, because like they are sort of trained on overlapping but sort of distinct data samples. So like, do we decouple that, because there would be different types of uncertainties?
Well, so there are two kinds of uncertainties, right? I mean, one, which is the uncertainty of your model, and other is the noise in your data, right? So, typically, practically the way you implement is you have the entire data set, you sample K different batches from the same data set, and then you feed each batch to each head, right? So, in expectation, each head ends up seeing the same data, but just the order in which the data is coming is different, right? So what I presented, maybe was a very, maybe it's a pedantic version of how you do bootstrapping, that you sample first and then you train, right? But if your data set is very large, you probably don't want to keep just sample once and then have K different sample data sets and then use them. So practically what you do is you just have the entire data set. At every step you would sample K batches, pass them into K heads, update, and repeat, right? So in that sense, in expectation, all the networks are seeing the same data, just in different orders. So therefore, what is, so then it is just the random initialization and the ordering, which is making the networks make different predictions, right? So the data set itself, in expectation is not different.
Okay, so but ordering matters. So it's like, is the random initialization the primary source of uncertainty there?
And the ordering also.
Okay, thanks.
Yeah, it is because because we are doing non-convex optimization with SGD, so the ordering ends up being important.
Thanks.
Okay, so let's move on. I think they were like these two nuggets. We'll have a couple of more nuggets in a future lecture on advanced deep learning, but let's hold on to that. These nuggets will come in useful in the next couple of lectures. So now let's move on and investigate some issues in reinforcement learning. So to illustrate that, consider this robotic system which has an observation and it has a couple of objects on a table, and I give a goal image in which the objects have been reconfigured into a different set of positions. And the question is, what actions can take me from the current observation to my goal? Right? Similarly, I could be trying to manipulate a rope and have a current observation and the observation of a goal and ask the same question. So, as we have looked in this course, reinforcement learning, tries to learn a policy which maps my states to actions. When I take an action, we end up in the next state. If the next state ends up being close to the goal state, we typically give a reward, and the whole game is to maximize the sum of rewards which the agent is collecting. But what is a catch, or what is an important point to note, is that these parameters theta of your neural network are initially random. And what that means is that initially, the actions that you're predicting are not meaningful. Right? They're essentially also random. So in order to get the reward, what we are hoping is that starting from the current state, I'm going to make a sequence of actions which is going to get me close to my goal state. Right. So in this particular example, how likely is it that you're going to do a sequence of actions which, starting from the current observation, is actually going to go and tie the knot? Right? I mean, it's highly unlikely this is going to happen by chance. And this is, exactly why, if you consider Atari games or even consider the game of Go, we got successes with reinforcement learning, but we required millions and millions of interactions. The reason is simply because you are hoping that if you do so many interactions, once in a while you'll get lucky and hit the reward, and that is going to bootstrap your learning, right? Because if you never hit a reward by random exploration, in that case, you know then there wouldn't be any gradients to modify the policy, and the policy will just remain random, right? So it's essential for you to hit the reward by just doing random exploration. And that's exactly why on these games you are requiring so many data points. And the second thing to note is, that in these games the reward function is very distinct and it's clearly provided. Right? For example, the game score over here is the reward signal. But in many practical settings, for example, if I'm trying to manipulate the rope, it's unclear what my reward signal should be. And so one thing I could say is, maybe I'm going to take some difference between these two images. But if I take this difference in the pixel space, it is not very meaningful. Now, why is that? Because I could just shift the rope, even if the rope had a knot, but it is shifted than my goal image, then my pixel difference is going to be super large, right? So in order to get a good reward function, one thing that you could do is to build a classifier which distinguishes any state from the goal state. But how do we build this classifier? We will end up getting annotations from humans, or we'll rely on a human farm to give us annotations that this state xt plus 1 is actually different from xg, or it is same as xg. And now if you were to change the goal, I'll have to repeat the process and learn one more classifier. So the point being, the policies that we are learning are actually task specific. right? They may not be able to generalize to new goals because just even getting the reward function for the new goal can be quite tough in the general setting. So in some ways the issues, some of the pressing issues with reinforcement learning is we require lots of data. It's unclear where do rewards come from, and the learned policies end up being task specific. So in the previous lecture, and even through the assignment that you're doing, right, we looked at how reward engineering might play or is critical to get reinforcement learning to work, right? And in the future lectures we're going to look at how inverse reinforcement learning or demonstrations can be used to overcome some issues associated with uh, measuring reward functions. But what we look in the next few lectures is this question of how can we improve the data efficiency of reinforcement learning systems, assuming the reward is well defined. So there are many techniques for this, many ideas for this. One idea is that collecting data in the real world is expensive, but what if I can collect data in simulation? That could be much cheaper. The other possibility is that we can transfer from other similar tasks. The other possibility is we can make use of expert demonstrations which can help us overcome some of the exploration issues. We can use models if they're available or learn models, or we can improve exploration through various methods. So pretty much the last three topics in this list are going to be three separate lectures that we will have going forward. In this lecture we will try to cover the first 2 points and see how simulators can help us improve or construct reinforcement learning systems which would be infeasible to do in the real world, and do a brief survey of different approaches for transfer learning and specifically problems associated with respect to transfer learning in context of reinforcement learning. So let's first jump to learning from simulators. But before I jump, I'll just take a small pause and see if anyone has any questions at this point. No, all clear. Okay, so let's talk about learning from simulators. So why is it a good idea to use simulators? For example, on the left side I'm showing you a traffic movement in a city. On the right side is simulated traffic movement. It is much easier to collect lots of data in simulation because I can run things in parallel, versus if I'm collecting data in the real world, I need to wait for a long period of time. So if I have parallel compute at my hand, or if the simulator is fast, I could easily collect large amounts of data, right? Second thing is exploration is going to be safe in simulations, right? I'm not really going to hurt something. Then sometimes in simulation it's possible to use some privileged information which may not be available in the real world, right? For example, if I'm driving a car in the real world, I might only know about the locations of cars which are near me, and I may not know the intention of the drivers in those cars. Versus in simulation, I have access to all of that information, right? So sometimes we can make use of this privileged information. Why is it privileged? Because it is not directly available in the real world. It must be inferred from observations. But in simulation, we have direct access to it, right? So that is why it is privileged information. If this does not make sense, give it a couple of slides and it will start making a lot more sense, because we look at privileged information in detail. But we also have one issue, that there are differences between simulators and the real world, which leads to some issues associated with transferring policies which are trained in simulators to the real world, which is typically referred to as the sim to real gap. And we will look at what is the state of art in addressing this concern. So let's start off by looking at a popular example, which was the Skew Manipulation, which was work done by OpenAI a couple of years ago. And what they demonstrated was, if I give a goal configuration of the cube, I can have this hand, like a real hand, reconfigure the cube in the configuration shown by the goal. But I mean, reconfigure it to a goal configuration which is provided by the human. So let's look at how this system was was set up, or how the system was trained. So a lot of the training of this system happened in simulation, right? So each of these is like a hand which was set up in simulation. And the way we trained the policy was, the input state was the fingertip positions and the object pose. And what they used was pretty much PPO with a recurrent network, in specific LSTM, to output actions, which is the motion of the fingers, right? So this is what was used to train the system. So over here, does someone wants to comment on whether fingertip positions or object pose, if either one of them is privileged information, or are both of them non-privileged information? So maybe let me put it another way, right? So the way to train these policies is, I get the pose of the object, I get the fingertip positions, and I use PPO to output actions, and we maximize the reward function, right? So in some ways, everything we know what an LSTM is from the last lecture. We know you have already implemented PPO as part of the assignment. So there is really nothing new over here, except the state description, right? And the state has two things: one is fingertip positions, and one is object pose. So in simulator, both of these variables are directly observed, or I can directly access the values of these things. But consider real world, right? In real world setups, which one of these is directly accessible and which needs to be inferred, maybe from some kind of sensor, so we don't have direct access to it. Anyone wants to comment? Nope. I guess I moved my next slide while trying to open the chat. But yes, so I guess the comment was, finger position is accessible, whereas object pose needs to be inferred from camera images. So why is fingertip directly accessible? Because in many robotic systems, there are motor encoders which are present, which can tell me exactly how much the finger moved. Whereas there is no good way to measure pose. I have a camera, I can look at an image, and I need to infer pose from the image. Right? So, what you end up doing is that first you train a policy with this privileged information. Then, you train a predictor which can go from images to predict this privileged information, right? For example, in this case, I can train a convolutional network which can take in the images of the hand and the object and predict the pose of the object, right? So in this way, the policy learning becomes easy because I have access to this extra information. And the reason I can do this is because I'm in simulation where I can directly observe this variable, but then I cannot function in the real world. So to function in the real world, I will train this separate classifier, which is able to get me to this privileged information. So, if you actually look at their setup, this is the setup that they end up having, where they have these, gazillions of camera, set up to measure, where the object is, for instance, and, even to improve the fingertip estimates. Right? So then you can put both of these things together. So we have the policy, which was trained using object pose and fingertip, and we train the perception system, which goes from real images to the object pose itself. So now what is the advantage of doing this? So the advantage is that when I'm training the reinforcement learning system, it is being trained from a very low dimensional state space, right? Because I'm not directly training with images. Now the advantage of this is that I'm going to increase my data efficiency quite a lot, right? And then the job of dealing with high dimensional sensory observations or images is just left to supervised learning, which in general is more data efficient than reinforcement learning, right? So this is one example where simulators have some more information that we can utilize to train RL policies, and then separately train some subsystem which can estimate that privileged information in the real world, as opposed to maybe directly feeding in images and fingertip locations and then trying to predict actions. That is much more challenging than breaking up the problem in this particular way. And if do this, use a massively scaled implementation of PPO, and you know wait for some large amount of time, then you end up learning these interesting strategies of manipulating the cube in many different ways to achieve the target goal configuration. Now I have one more example on use of privileged information, but before I step into it, I want to take a small pause and see if there are any questions on this part. Nope. Okay, so let's march ahead, and maybe if you have more questions, we can look into it. So a second example, I want to bring up is this quadrupled motion. So this is a paper which was published last year, and this robotic system is walking in the real world, and it is walking through a diverse range of terrains. Turns out that the system was completely trained in simulation and then deployed in the real world. Right? So let's look at how this was made possible. So we have a simulation environment where we generate random terrains, But in simulation, we have access to some information, right? For example, whether the legs are in contact with the ground, what is the contact forces, what are the friction coefficients, and so on, right? So these things are measurable in simulation, but not necessarily in the real world, right? So we can feed in this privileged information into a neural network to output actions, and we can train them by some reinforcement learning algorithm. Like again, I believe this was PPO in this case. And what they call this policy trained with such privileged information as teacher policy training. But obviously, we don't have access to this privileged information in the real world. So what do we do? What we do is, we have, some readings on the foot, which, they're referring to proprioceptive readings. What does proprioception means? Typically it means two things. So one is your knowledge of how much your actuators are moving. For example, if I move my hand, I also know how much I move my hand, right? So that's part of proprioception. The other thing is you could have force sensors on, your feet, or for example on my skin, have force sensors which can make me feel touch. So both knowledge of how much you moved plus, any kind of force sensing is typically part of proprioception, right? So this is something that we can measure, right? So now what they do is, so they say, well, this is so I can measure proprioceptive information at previous n time steps, and we're going to use that as a state representation, put that into a neural network, and then predict the action which the teacher policy learned. Right? So teacher policy was learned using reinforcement learning, and it is easy to learn it because I have access to privileged information. If I did reinforcement learning from this proprioceptive information, it might be much harder. So what I do is, instead of doing reinforcement learning, I end up doing supervised learning, where supervision for action ends up coming from the teacher policy. Right? And if you end up doing these, things, turns out that you can train this system purely in simulation and then transfer to the real world. Now, there is one more aspect of how do we create these terrains, which is also critical for transfer. Now, that is something I'm not talking about now, but we are going to discuss this in a later lecture. But what I'm trying, the takeaway over here is, for you to understand what is privileged information and how we can leverage privileged information to train reinforcement learning in a more data efficient setting, or to make it work where, if we did not have privileged information, maybe the system will completely fail, right? It may not even learn. But because we can be clever sometimes, we can make use of this extra information we have. So any questions on this part? Well, if not, then let's move ahead. So so one thing is, okay, we have trained these policies in simulation, but now we need to deploy them in the real system. So now the question is, if I'm trying to transfer from simulation to the real world, then what ends up happening, right? So for this, we have a small poll which I just launched. So I encourage all of you to maybe look at this poll and answer it, right? So the poll is asking, transferring policies from simulation to real world, is it easy, is it hard? If it is hard, why is it hard? Or if it is easy, why is it easy? Right, so let's give it maybe 15 more seconds, and then we're going to stop the polls. I see there are maybe 17 people who answered, maybe a couple more. Okay. Okay, so I think like the jury is in. So, let's see what people think. So I'm going to end the poll and share the results, right? So it seems like, most people think that transferring policies from simulation to real world is hard because we don't know the precise value of the physical parameters. Right? So, one more option is, which received 3 votes, is it is hard because we don't know the exact laws. So it turns out, because we are not dealing, with some quantum phenomena. I mean, we are dealing with, like some classical mechanics over here pretty much. We know the laws, but what is really hard is to implement those laws because we don't know the exact values of, say, the friction coefficient or the mass of the robot or the inertia of the robot and so on, right? The one thing you might say is, well, what happens if some of the uh, if the robot is not rigid but non-rigid, right? In that case, you know I mean, do we still know the exact laws? I think we know the exact laws, but it's just that it's very, very hard or very computationally intensive to simulate it, right? And sometimes there are, if you have motors, right, motors don't behave as ideal motors, but there are some losses which are there, and it's hard to model those losses because, again, we are not able to record everything about the motor. For example, how much friction is there as the motor rotates, for example, right? So we don't know how much loss it's going to incur, right? So does that make sense? Or if people who answered none of the above, or who answered because we don't know exact laws, does that maybe satisfy you, or answer maybe what you were thinking, right? I mean, if not, feel free to bring up on the chat. But the main reason why simulation to real world is hard because exact physical parameters are unknown on the real system, right? So one idea which is used to bridge this gap is to say, well, I don't know the exact parameters, so what about I train with many different parameters in simulation and hope that one of those parameter settings is going to be close to the real world, right? For example, I might have a good estimate that the friction coefficient is between zero point 0.1 to zero point 0.5, but I don't know the exact value. So maybe I can train, policies with different friction coefficients, maybe one with zero point 0.1, maybe one with zero point 0.5, or, and then I can, deploy one of those policies in the real world. Right? So, this idea, is popularly known as domain randomization. For the way it ends up working is I take a particular environment and I create many instances of it. And these instances can vary through different ways, right? For example, I could change the camera angle, I can change the color, I can change the friction coefficient, I can change the mass of the objects. And then we will learn a single policy which can work through all these different variants of the training environment. And the hope is, because we have trained on a large diversity of environments, my testing environment, which is the real world, maybe close to one of these samples in the training set. And therefore, we are going to be able to transfer to this test set. Right? And what we're really interested is how good the test performance is, right? We pretty much don't care about the training performance so much as we care about the test performance. So this approach of creating these variations in the training environment and then learning one policy which is consistent across all of these variations is called as domain randomization. Right? So, for example, if I want to manipulate cubes, what is being varied over here, as I said, it's like position, shape, and color of objects, material texture, lighting condition. We can also add random noise to images, change the field of view of the cameras, and so on, right? Or in another case, maybe I'm trying for this robot to reach and pick up some items. So in simulator, I could vary the mass and dimensions of the object, of the robot, and then different like parameters like the damping coefficient of the joints, gain for the PID controllers. There are also delays which happen, between the time I output a command to when it is applied on the physical system, right? So these are all things that we can randomize and then train over. So any questions on what domain randomization is? Right. Well, if you have, feel free to put in the chat. I'm just going to walk through some more examples. So this is a video of a pose detection system which came out some time back. So what they're trying to do is to measure, what is the orientation of these different objects, right? And they're trying to measure the 6 degrees of freedom pose, which is 3 degrees for rotation and 3 degrees for translation. And how do they train the system? In simulator, if I have 3D models of objects, I know their exact pose. So now I can put these objects, with these random, backgrounds, or I can, put them in naturalistic backgrounds, and then I can predict from these images what is the pose. Right. So this is again an example of, augmenting my data set with much more variation. Because if I just had these 3D models and I put them against clean backgrounds and train on them, and I hope it is going to transfer to natural images, that's not going to happen. Right. So instead, what we do is, we put these objects on natural images in many, many different poses, and then train a classifier to predict the pose from it. Similarly, in the object manipulation setup that we were looking at, right? So these to make uh, this task of going from images to the cube position, and also because we don't exactly know all the parameters of the hand in the real world, there was domain randomization again implemented. So over here, what you're showing is some domain randomization, which was visual in nature, but there was also other domain randomization for, like the friction and so on and so forth. I mean, those motor parameters, right? So, so let's try to understand, in slightly more detail, what domain randomization is doing. So to do that, let's consider that I have PyRand, which is a policy trained with multiple randomizations. And then we have PySingle, which is policy trained with just one parameter settings, right? So what do I mean by one parameter setting? Instead of training on many different randomizations, I just choose one values in simulators in the simulation and only train my policy on that, right? And let's try to answer some of these questions. So the first question is, will PyRand train faster than PySingle? Right. So again, we have a poll for this, right? So I'm going to launch the poll and see, what people have to say, right? So if, yeah, so let's, maybe give, 30 more seconds to see what people are saying over here. So I think if you're on the fence now, probably it's a good time to commit. Okay, I have 17 votes, maybe waiting for a couple more. We have 18. So let's, I'm going to end the poll in 5. Okay, so let's see what people have to say. I'm going to share the results. It seems like, 14 people think that no, it is going to train slower, and 5 people think yes. So maybe, one of the person who voted no, do you want to maybe comment on why PyRAND will train slower?
Um, because the policy has to generalize to a lot of the parameters, so it's likely that it's going to take more time, I guess.
Right. So over here, because the policy has to deal with many more parameters, right? It needs to, fit many more, a lot more variation, and it can take much more time to converge to a stable, or it might take much more data to get the same performance, right? Just because I have to abstract out all of these variations which I'm training with. So, okay, in the same vein, a second question is, will PyRAND converge to higher reward than Pi single? Right? And we are talking about the train time reward. So, again, we have a small poll for this, right? So I'm going to launch the poll and let's see, what we have to say. So, I mean, mhm. Okay, so I think the answers are trickling in. I'm going to take 5 more seconds and then call the poll off. So if you're still on the fence, now it's the time to make a choice. Well, I'm going to end the poll now. So let's see what people thought. So this time it seems it's much more split, where 12 people think that yes, it will converge to a higher reward, and 7 people think no, it will not. Right, so maybe someone who said no, do you want to comment on why it will not converge to a higher reward? So I see something on the chat. So one comment on the chat is that PyRAND has to learn a robust policy, and the policy has to be robust against all the parameters, and therefore it cannot achieve a high reward, versus a single policy versus Pi single can just overfit to one parameter setups and therefore end up achieving higher reward, right? So that is largely true, right? So if you just have one parameter setup, it's very easy to overfit to that one parameter setting, right? And therefore you can achieve much higher reward, versus if you have to learn a policy which needs to fit in across a bunch of parameters, right? So the answer is, no, it's not going to converge to a higher reward in this particular scenario, right? And an obvious next question is, will pi rand generalize better than pi single, right? So now we are talking about test time performance, right? So again, we have a small poll for this, so I'm going to launch, right? So what so is there any benefit at testing time for doing this randomization, right? So it seems like I've got 14 votes. Maybe some people are still on the fence. If you're still there, I would say maybe just commit to what your gut feeling is. So I'm going to close this in 5 seconds. Okay, so I'm going to close it now. So it seems like in this one everyone agrees that pi rand will actually generalize better than pi single, right? I mean, this was the whole point of doing domain randomization, is that we can generalize to a new parameter setup, where a new parameter setup is the parameter setup in the real world, right? So just to show these, just to answer these questions in context of a real world experiment, so what I'm showing you is the training curves from the domain randomization, which was done for this Skew Manipulation task, which the videos we just saw, right? So the red curve is the curve which is trained with no randomizations, right? And the y-axis is some measure of reward, and x-axis is the hours of training. And the blue curve is the curve which was trained with all randomizations, right? So as you can see, the red curves learns faster, but also ends up achieving a higher reward, versus the blue curves learns slower. It actually ends up achieving a lower training reward, but it generalizes much better, right? This is the same, the same set of questions that we answered in the previous slide. This is just illustrating, what we took away in context of a real experiment which was conducted. So any questions, or any comments or thoughts on domain randomization? No? Okay, so let's march ahead. So okay, when we can do domain randomization to maybe transfer from simulation to real world, but surely there's no free lunch. I'm doing randomization, right? So what I want is my policy to become robust to a large number of parameter setups instead of this one specific parameter setup which is there in the real world, right? If I knew that parameters, then I can overfit to it, and that would be the right kind of overfitting that we would want, right? So it turns out that if I train a policy without randomization, which is say the blue line, so the y-axis is the return, and the x-axis is the say some value of a particular parameter, body inertia over here. So if my body inertia in simulation matches the real world, I get good performance, or if I'm close to it, my performance is good. But if the body inertia deviates in the real world too much from simulation, the performance is much worse, right? So this is what would happen if you train with maybe a single parameter setting. In comparison, if we train with domain randomization, which is a red line, what that means is, I can train with a bunch of different body inertias. Then what you see is the line is quite flat, right? So I am able to generalize to many more body inertias. So maybe I'm going to generalize better to the real world, but my peak performance is going to be lower. So in a way, there's a trade-off between robustness and peak performance. So domain randomization comes at a cost. And this cost is that my peak performance is going to be lower. So a natural question is, how do we overcome this limitation? Right, and I see, maybe there's a question or a comment popping up. So one question is, if the parameter space is small, we could sweep it. So yes, but what that would mean is that we will have to do a real world experiment for every parameter setup, and that can be expensive, right? So I mean, if it is only a couple of values, maybe that's possible, but in general, that might be hard to do. So now, let's look at how we can overcome these issues, right? So before we jump into it, I'm just going to take maybe a minute's pause and let you just think about this for some time, and let's resume in a minute, right? I'll just be back in a minute. Let's resume. So one suggestion which has popped up is maybe let's randomize this, but over a distribution rather than uniformly, right? Which I think is a good intuition, that maybe we don't want to uniformly sample all parameters, but choose what or choose a specific setting of randomization, right? For example, maybe I have some prior knowledge that my body inertia is going to be within this range. So instead of choosing a wide range, I could just choose that small range. And in but in some cases we may not have access to this prior knowledge. So what do we do then, right? So some so there are a couple of methods which are being developed. I'm just going to tell you about a couple of them. So one possibility is that I can actually try to predict the simulator parameters that one should be using. So instead of randomizing, I have a policy which predicts the simulator parameters. Now I have a simulator with those fixed parameters which was predicted by the policy. Then I train whatever I want to train, maybe through imitation learning or reinforcement learning, and I train my policy using the simulator. And then the reward that I end up getting over here is used to train the policy to set the parameters of the simulator. So essentially what we are saying is we don't know what good settings for the simulator are. So I am going to just predict the simulator parameters, right? So this is one approach we could be following, right? So it's we directly learn how to randomize the simulator. In a similar spirit, maybe there are different kinds of randomizations we could do. For example, if I have images that we are learning with, so these are my environment observations, which was my actual ground truth image. I modify them by the cropping them, grayscale, flip, rotate, and so on. I suppose I have a bunch of randomizations that I need to choose from, right? So how do I make that choice? So one way to think about this is that this is like the exploration exploitation trade-off, right? So some parameter settings are going to lead to high rewards, but some of those, but I don't know if I could come up with better randomizations, right? Or should I just choose the randomizations which I have right now? Let's suppose I choose one setup of randomization. Let's suppose I say cropping is more important than doing flipping, and maybe rotating is more important than doing grayscale, right? So should I stick with those randomizations, or should I try some other combination, right? So why are we trying to do these combinations instead of uniformly going over all augmentations? Because uniform augmentation or randomization can hurt peak performance. So, one idea, that we can leverage is how to find the optimal exploration exploitation trade-off is by doing UCB, right? So we discussed UCB in case of bandits. So you can think of each one of these augmentation as one arm in the bandit, right? And then we can choose, which augmentation to use by using the rewards that I am getting, and then do UCB to get a distribution of, or like, a probability distribution on this augmentation. So this was, recently proposed, last year again. It's called automatic data augmentation. Right? Any questions on this part? Nope. Okay. And we can also empirically look at the results. So what these graphs are showing is, PPO is shown in dark blue. Then if you just do uniform randomization, with that is the orange and the red lines, right? So sometimes uniform randomization can really hurt performance. And the light blue and the pink lines are what you get if you do this adaptive augmentation, right? So this adaptive augmentation is helpful and certainly is better than uniform domain augmentation, which can sometimes really hurt if you make the range be really large, or if the range that you randomize over is mismatched from the testing set of parameters. Right? Yet another idea is to say, well, I'm going to randomize the simulation, by changing some things, but I'm going to learn some neural network which transforms this randomized image into some canonical image. And then I'm going to train my policy on this. So what I'm learning is from different randomized versions of the simulator, I'm trying to map them into some canonical frame of reference, right? So that if I get my real world sample, I can also map it to the same canonical frame where I can then run my policy, right? So instead of learning a policy which works across or is robust to different augmentations, what I can say is, well, I'm going to generate multiple augmentations, but learn something which maps these augmentations to a canonical frame, and then learn a policy on the canonical frame, right? So, you can expect that this is going to have a better trade-off for robustness versus peak performance, right? Because my policy is trained just on the canonical frame. Right? So this is another method which was proposed maybe 2 years ago. Then, another thing which, you could do if you have the luxury of collecting significant or at least some amount of real world data is to say, suppose I train my policy in simulation, then I apply this policy in the real world, and I get these trajectories which I get in simulation, and I get trajectories in the real world. Then what we can do is we can take these trajectories and say how to modify the simulator so that if I apply the same sequence of actions, then my trajectory in simulation and the trajectory in the real world should come as close to each other as possible. Right? So we are trying or we are learning to adapt the simulator to reality. Right? Now, what's the drawback? The drawback is that we still need to collect real world data, and that is essentially part of the training over here. So any question on some of these methods, that we have discussed over here on, sim to real transfer? No. Okay. So until now, what we looked at was how, if we are training policies in simulation, we can transfer them in the real world. Right? And the next assignment, which will be coming out shortly, is going to be focused on giving you a practical experience with this sim to real issue. Right? And what we will be looking in the next lecture is, we'll start off with transfer learning, where the goal is, instead of transferring from simulation, if there were other real world tasks that I've trained my policy on, how can I leverage that knowledge to improve my performance or to improve my data efficiency? Right? So typically when people talk about data efficiency, they refer to how many data samples were collected in the real world. Many times they discount the amount of samples which are collected in simulation, because simulation examples can be cheap in many scenarios. So with that, I'm going to stop for today and happy to take any questions which are there. So